over 6 million now? 6 million cases, I think. Staggering right now, I know that.
We're not 6 million.
So like I said, kids, last section that we're going to talk about in chapter 1, over all the functions we've dealt with, is going to be dealing with exponential functions. And this is going to kind of tie into some of the exponents that we've worked with and some of the radical and rational exponents that we worked with. But that's a pretty good example of exponential growth right there. I've told kids that if you go to Las Vegas, if you bet $1 the first day and win, get out of there. Come back the next day, double your bet. And keep playing until you win. You know if you did that, you know how much money you would have in 3 weeks' time? Anybody know how much money they'd have in 3 weeks' time? If you stayed there 3 weeks and doubled your bet, if you could just double your winnings every day, starting out with $1 each day, you would be close to 2.1 million in your hands. So, in 3 weeks we could make $2.1 million.
Why don't people do that?
Should we go?
Yeah.
All right, Sam, I'll tell you why people don't do that. 2 reasons. One, to win that kind of money, you've got to be willing to bet that kind of money or have that amount of money, okay? Because eventually I want to get $2 million total, right? But eventually I'm going to have to put down a $2 million bet. I don't have $2 million laying around. So I've got to find a creditor that's going to back me on that. No one's going to do that for you. That makes sense?
Yeah.
So, unless you want to loan me the money, then I'll go. And then we'll split it 50-50.
60-40.
60-40, fine. I'll take 60, you have 40. I like that deal.
No, that's
Oh, okay.
no.
That's pretty interesting how that stuff works. But yeah, numbers like that kind of fascinate me. And then this idea of exponential growth with all the COVID that's going on, it's been really interesting for me to watch a lot of the graphs and stuff on the news. So we're going to kind of touch on some of that today. Exponential functions. What are some of the characteristics of the graph of an exponential function? How many of you guys have heard of exponential before? Things are growing exponentially. Where are my people in science class? You talk about cells being cut in half at all for anything? You guys are looking at me like you don't know what I'm talking about. What happens to cells as the body grows? They multiply. 1 turns into what? 2. Then 2 will turn into what? 4. Then 4 will turn into, and it just keeps multiplying like that over and over and over. And that's exactly what exponential growth is and exponential decay is. So we're going to talk about this right here. Graph of exponential growth and exponential decay functions. We're going to work on writing exponential models and recursive rules. This is kind of a tough one right here, okay? Kids struggle with this because it's new. And then we'll look at rewriting some exponential functions. But first of all, we need to understand some terms. How about I volunteer to read my first vocab word up there, exponential function? Who wants to volunteer to read that? Don't be shy. I'll take the first one. A nonlinear function of the form y equals a times b to the what? A cannot equal what? B cannot be what? And b has to be greater than what? Okay. Anytime you have an exponential functions start out from the left to right. They start out kind of slow, and then they blow up like this. That's what an exponential function looks like graphically. Okay. An example would be something like this: y equals 3 times maybe, I don't know, 6 to the x power, like this. Okay? This is considered exponential growth because in this form right here, y equals a times b to the x. What value is a? 3, not equal to 0. What value is b? If this b value is greater than 0, this indicates exponential growth right here. And we'll talk about that here in a second. But that would be an example right there. All right? So an exponential growth function right here, this is the big idea. B has to be greater than 0. So on this up here, it says for an exponential growth function, it's of the form, and there's a lot of formulas that we'll talk about and we'll come back to. But underline this, y equals a times 1 plus r to the t. Again, a has to be greater than 0 and r has to be greater than 0. Or y equals ab to the x, where a is greater than 0 and b is greater than 1. I'm going to go back with this right here, kids. Examples. What's the b value there? 4. Is 4 greater than 1? Anytime in that form, when you have a b value greater than 1, that's going to indicate growth. Okay? That's going to indicate growth. Now, another one right here is another formula. This R is typically like a percentage rate. So R is typically a percent in problems like this. So when we talk about real life problems, you might see something written as y equals maybe like 2 times 1 plus, I don't know, 0.08 to the t power also. Guys, in parentheses, what is 1 plus 0.08? 1.08. And is that 1.08 bigger than 1? Is 1.08 going to be bigger than 1? So if I have anything in parentheses like that that's bigger than, I screwed this up, kids. This should be b is greater than, I made a mistake here. This should be b is greater than 1. Anytime that part in parentheses for these functions is greater than 1, then what type of function do you have here?
Growth.
Growth! Yes, growth! Whew. And it's going to start out kind of flat like this, and eventually over time it's going to blow up. Okay? Now, we say that things are going to change by a growth factor, and the growth factor is simply the what? The value of b in there. Okay? What's the b value in this? Therefore, the growth factor is what? 4. You're just multiplying by 4 over and over. What's the growth factor here?
6.
What's the growth factor there?
1.8.
1.08. Okay? So growth factor, simply the b value. All right, so I kind of cheated this a little bit. Asymptote. Anybody have you heard the word asymptote? I dare you to walk up to somebody and kind of a mad, kind of just like mean mood and just call them an asymptote sometimes and see what they look like. If I walked up to somebody and said, "You're an asymptote," do you think they would perceive that as a compliment or something else?
They'd be confused.
Yeah, something else. Okay. Asymptote's a funny word. Anybody know what an asymptote is? Okay, there's a paradox out there called Zeno's paradox. You know what Zeno's paradox is? Have you ever heard of Zeno's paradox? Okay, I'm standing along this wall, and I'm going to go to that wall. But the rules to the game are this, and you guys have to watch me do this hour, okay? You can't leave until I get this done. Deal? Shouldn't take very long. All I'm doing is going to that wall. From this wall to that wall. I mean, you guys can't leave until I'm done. Does that make sense? Okay, so the rules are this. I start here. I can only go halfway. All right. Is this about halfway, Allie? Okay. Now I'm stuck. I made it halfway there. Now from here to there, I can only go halfway there again. All right, we're getting close. This shouldn't take very long, should it? Now from here to there, I can only go half this distance. Okay, now go half that distance. Now go half that distance. I'm getting close, guys. Oh, you said something. What was that?
You're never going to get there.
Why am I never going to get there?
You're only doing half the distance.
You want half the distance. So if I go half of the previous distance all the time, am I ever going to get to that wall? I'm going to have to look at that wall like infinitely as close as I possibly can. Okay? And you'll never get there. Okay? And that's kind of what an asymptote is. It's like a line in the coordinate plane that a graph will never cross. And in this example up here, can you guys see that okay in your notes? See how this graph is blue right here? Doesn't it look like the blue line is right on the x-axis right down in here? But the truth is, it gets really, really close to the x-axis, but it never ever crosses it. So it says right here, the x-axis is an asymptote of this graph. So this graph, the further left I go, does it ever cross the x-axis? The answer is no, but it just keeps getting closer and closer and closer to it, but it never ever really gets there. Okay? So an asymptote is like a line that the graph will never ever cross. And we'll talk more about that in some examples. Okay? All right. Guys, just like there's exponential growth, there's also exponential, what's the word here? Decay. And this time, instead of b being greater than 1, b is what?
Less than one.
Less than 1. All right, so an example might be like this. Y equals... You got to give them credit. They're pretty lively on a Monday morning first hour over there. Why is that exponential decay, kids?
Because it's a factor of less than 1.
Yeah, so I started with what value? You start with 2, right? And we're constantly taking 2 and cutting it in half. We're multiplying by half all the time. And we'll talk about this in the sequence when we start looking at that stuff, all right? You also might see it as something like this. Y equals, and this will work with percentage rates, like 2 times 1, whoops, like a 1 minus an r to the t power also. Now don't worry about the letters right now, but that r typically stands for a percentage rate, and that t is going to be something that's measured in time. And then right here, kids, your decay factor. Again, the decay factor is what?
Plus b.
It's just your b value, okay? So if I ask you, in this case right up here, what's your decay factor? You're going to tell me it is 1/2. So suppose I wrote this. Suppose I wrote y equals 7 to start with times, I don't know, 1/3 to the t power. What's your decay? Well, first of all, is that growth or decay?
Decay.
Why is it going to be decay? This value right here is less than 1. That b factor is less than 1. And if I ask this question, what is the decay factor? You would say
Start at 7.
1/3. So if I say we're taking 1/3 of stuff, if I'm taking 1/3 of something, am I making it bigger or am I making it smaller? Exactly. Okay. And then, guys, the one I'm pretty concerned about right here, but I don't know how much we're going to touch on it here today, is what's known as a recursive rule. And this here is going to be very new for you. How many of you guys have heard of recursive rules before? That's good. You should have by now. Okay. A recursive rule is going to be a rule that gives the initial value of the function. Okay. Initial meaning the start value. And we talk about recursive rule here because in a function like this is like saying y starts out at what value right here? 7, and then you're going to multiply it by 1/3 over and over and over, or t times, okay? So you're always going to know the initial value, f of 0, and a recursive equation that tells how the value f of n is related to a preceding value, f of n minus 1, okay? Here's what I always call this stuff. I say, what do you always start with? And then what would be next, okay? If you can think of recursive rule says, what are we starting with, and then what comes next, I think this will make sense to you, okay? And again, for now, just get the vocabulary down. We'll look at examples that come with this, but this recursive rule, what do you start with? What comes next? That's kind of what this means, okay? All right, take a look at the page right here. Anybody need more time getting any of that stuff down? A lot of information here today. Questions so far? All right, my friends, let's move on to page 2. Here we go. Oh gosh, we still have more. We still have more vocabulary. Oh my goodness is right. Sequences. I think you know what this is. This sequence right here, what was happening in my sequence?
Doubling.
Always doubling. So anytime you're looking at a sequence or an ordered list of numbers, you're always looking for some kind of a pattern. Sequences are ordered lists of numbers. So right up here, guys, 5, 10, 15, 20. What's going to come next? 25. So what's the pattern?
Adding 5.
Adding 5 to the previous value. Okay? This is kind of like that recursive thing. What do we start with? 5, and then what we do to the next is add 5 each time. So the next one is 5 more than what you're at now. Start with 2, 4, 8, 16. What's next?
32.
32. What's the pattern?
Times 2.
Okay. And now we're also going to look at properties of exponents. There's going to be some 1.5 rules and some 1.4 rules to remember. I think you guys did an awesome job in 1.4 and 1.5 based on what I've seen. So I feel really good about that. So don't forget about our rules of exponents, okay? All right, let's rock. Core concept. We've kind of talked about this already. This is a parent function that indicates what, kids?
Exponential growth.
Okay, exponential growth. It says the graph rises from left to what? Right, passing through the points 0, 1, and 1b. I have a quick question here, guys. The x-axis is considered a what? How do you say that word, kids? Asymptote. Asymptote. You'll probably walk out of here and say, man, that person's such an asymptote. Can't take it anymore. Right? Is this line ever going to cross the x-axis down here?
No.
Nope. Okay. Here's how I think of exponential growth. Think about always looking at graphs left to right. If I go left to right, is this an uphill graph or downhill graph? Uphill graphs are going to show growth. What kind of graph is this as I move left to right? Downhill graph. And they talk about all this right here. This is going to be decay because b would be between 0 and 1. This would be growth because b is going to be greater than 1. So let's talk graphing an exponential function. And I'm going to run into decimals over here in a second. But kids, that first function right up there. Talk to me. It says tell whether each function represents exponential growth or decay, then graph the function. And I'm not going to get too excited about graphing. I'm going to put a little shortcut up here. Guys, is there any value out in front of this 1.3 at all in parentheses? So do you guys agree that this is really 1 times 1.3 to the x right here? Would you agree with that? Yeah. Okay. This is going to show growth or decay, kids. Why growth, Allie? Gracie, are you bringing her around?
Psych, what is wrong with them? I'm seriously about to go knock the door.
Open the door.
Yeah.
Fight.
You just need a
Door. I
teacher.
want to see what's going on.
We need to see if there's even a teacher in there.
Oh, I'm sure there is. He'll be good. All right, I want to show some characteristics of this graph right here. Do you guys all agree growth because 1.3 is greater than 1? Okay, let me check this out. I want to show you something real quickly. They must think math is exciting.
Whose room is that?
I love it. I'm starting to wonder if there's a cow over there having birth or something, because it's kind of scary.
I haven't heard a teacher yell at all. Like,
I'm just hearing sit.
yeah, me too.
All right, help me out, kiddos. What was the function again? Y equals 1.3 to the x power, is that right?
Yeah.
All right, kids, in decimals. I want to just show you some characteristics here real quickly. Make some relations here. Y equals 1.3 to the x, right? I'm going to type it as 1 times 1.3 to the x like that. I always think you should have an a and a b value in there. And if they didn't give you that a value up front like that, you have to assume it's what value up front, kids?
1.
Okay, 1.3. And then you raise it to a power by hitting the a to the b button, and I'm going to punch in x. Okay, first things first, kids. Does this graph confirm what we thought about the shape in terms of growth or decay? Okay, what is this point right here? 0, comma what? 1. Okay, I'm going to go to the point 1, comma something right here. When x is 1, what do you notice about the, did you guys see that?
Yeah, 0, 0.
Did you guys see that point 1, comma 1.3? Okay, here's the deal, guys. Anytime you're dealing with this right here, this point right here, this is always your start point, 0, comma what? 1. What if I would change this to a 2 out in front? Where's your start point? Okay, does that make sense? Guys, what's 1.3 times 2? 2.6, right? What if I change that 2 out front to a 3? Where's it going to start? Starts on the y-axis at 0, 3. Anybody know what 3 times 1.3 is?
3.9.
See how to get those first 2 points? Okay. So there's the graph. When they say graph it, I'm not going to get too excited about it, all right? You know where to go for that. You cool with that?
The graph is basically confirmation of things that you said. So you guys tell me in this next one right here, oh, whoops. Is there any value out in front? So really, where are we starting at?
0.
1 times 1/3 to the x. Talk to me, kids. Growth or decay? Decay. Because that b value is going to be greater than 1 or greater than 0, but less than what? 1. This would be uphill graph or downhill graph, kids? Let's check. So it was 1 times, and I'm just going to get rid of this. And what was it, 1/3 in there, kids? Does that confirm what we thought right there? By the way, where does this start? Anybody want to guess what point this is going to be right here? 1 comma something. Is it 1/3, 0.333 repeating? Okay. You guys feeling okay with that? If I ask you to identify growth and decay, can you do it? All right, let's move. Oh, I like this second
They
example.
are obviously not moving or doing anything.
Yeah, don't worry about them. We're good. We're good. Focus on what we do. Because you know why? You know why? You know who has the best first hour in the whole school?
Parson.
Mr. Parson does.
Because we
Okay.
don't talk.
I love this group of kids. This is fun. I really enjoy teaching this. I know you guys might not echo that sentiment, but I really enjoy teaching you guys. I've been impressed with what you guys have done so far. So keep up the good work. If I haven't told you that already, keep it up. I really enjoy this. How about a volunteer to read number 2 for me? Anyone want to do that for me? Don't know how to read, Gracie? That's okay. English, I ain't so good at English either. Sam, you want to read that for me, buddy?
Yep.
Just up above the 2 boxes.
Yep. The population of the city was about 1.04 million on January 1st of 2000. The population at the beginning of each subsequent year increased by about 2.05%.
Okay, so we have a population that started out where, kids?
1.04 million.
Okay, population starts at 1.04 million, okay? Is the population increasing or decreasing?
Increasing.
So are we modeling something that might show growth or decay here?
Growth.
Okay, let's talk about what's going on here. First thing it says, write an exponential growth model that represents the population of Y in millions T years after January 1, 2000. It says, find and interpret the Y value when T is 8.5. Now guys, I'm going to go back to something right here. You don't need to do this, just pay attention up here. I'm going to go back to this exponential growth function here, okay? Anytime you have something that involves a percentage rate right here, you're going to use this type of form right here. Either Y equals A times 1 plus R to the T or A times 1 minus R to the T. And since we're talking about increasing a population, we're going to use this one, okay? Anytime you use something with a percentage rate, this is what you use. So here's how this is going to work here. Right down here, I'm going to say use Y equals A times 1 plus R to the T power. Okay, here's what I want you to know. The A value is always like your starting value. So my question to you then is this. What is the starting value for population? 1 point. Say it one more time, Ellen. 1 point, not 4, but 1 point.
Oh, 1.0.
There you go. Okay, I just wanted to make sure I was hearing you correctly. You got it. 1.04. So in for A, we're going to plug in what value? 1.04. Got A value, and I'm going to write it down here. A is always like your start value. Okay? Then, it said the population was growing by how much, kids, per year? What percentage? 2.05%. Now you have to be careful on this. R is always listed as a percent. We need to make sure that we plug that in not as a percent, but rather as a decimal. So talk to me about this 2.05% over here on the end. Guys, that 2.05%, what's that going to look like as a decimal? Be careful. What do I have to do with the decimal? 2 to the left to make that a decimal? So this becomes times 1 plus 0.0205. Are you guys buying what I'm selling there? Okay, now what are we asked to find, kids? Find and interpret the y value when t is what? Okay. Oh, here we go. This becomes y equals 1.04. Guys, is it okay if I call this 1.0205 now? What am I going to put in for my time t? How many again, Allie? 8.5 years. All right, now I have a question. Do you all have your calculators handy right now? Because here's the deal. This is easy to evaluate. If you type in, just like I have, start with 1.04 in your calculator, and then type in a parenthesis, and then put 1.0205 in parentheses, and then raise that to the 8.5 power, you should have an answer here. I'm actually going to punch this up too, just to see that we agree. It says find and interpret the y value when t is what? Is it 8.5? Did you guys get something close to that? How many got 1.23 blah blah blah? Is that what you're getting? Did you do something different, Blake?
Yeah,
What did you get, kiddo?
1.18, a bunch of numbers.
What kind of calculator do you have?
There's another one.
Do the parenthesis part first. So go in your phone, do this. I want to make sure we all get the right number. Type in the 1.0205 first. Now raise that to the 8.5 power. You got a number there? Now take that number times what's out front here, times the 1.04.
Yeah,
Does that get you about that 1.235, whatever?
yep.
Now, is there anybody not getting that value right now? Are we all getting that? Okay, so the question becomes this. Find and interpret this. Well, what did y equal? Let's go ahead and round it to about y equals 1.24. So what's that mean, kids? What's that 1.24 represent?
Growth in the city population.
Perfect. It's growth. It's definitely growth. I like that, Gage. When did this problem start? 2000. And then t equal 8.5 years. That means 8.5 years after what year? 2000, the population was what? Yeah, so I'm just going to kind of bring this all together in this. This means that the population let's see, 8.5 years. Would you agree it would be 2008 then? And wouldn't 8.5 years be about the middle of 2008? Population in mid 2008 was how many people, kids?
1.23 million.
You okay with that? Now, the next part says what, kids?
Why isn't it 1.24?
Did I not round correctly? Oh, that's what I had here, wasn't it? I made a mistake, didn't I? Who called me out on that? Who said that? Gage, was that you? Was it you? I can't. All you guys are incognito right now. I don't know who's saying what. You know, your hoodies and your masks and everything. Yes, it should be 1.24. Is that okay, guys? Gage, thanks for catching that. I appreciate it. I make lots of mistakes up here, so anytime you catch me making mistakes, don't hesitate to yell at me. Thanks, Gage. Give yourself a pat on the back for that. All right. This next one's a little more difficult because it says to do what, kids? Well, let's just look at this right here. We knew in 8.5 years the population got to what? Well, we want to know how long it takes to get all the way up to what? Well, it's got to be more than how many years then? Got to be more than 8.5. So here's what I'm going to suggest. Let's use decimals with this here. All right, and I'll show you how we use decimals with this. So I'm going to jump in here. Guys, tell me what the function was for this right here. We had y equaled, what did we start out with? Was it 1.04? And then what was our growth factor? What did that add up to be? 1.0205. Okay, now watch what I do here with this, kids. We know that this is going to take more than 8.5 years, right? But we want our population to reach how many million? Watch this right here. I'm going to zoom in once. I don't know if that was a good idea or not. I'm going to zoom out, actually. We want our population Y to get to, you said 1.3 million? Okay, what I've done, this blue line represents a constant population of 1.3. The population was below it. It's getting closer and closer and closer. And finally, right here, what happens to these two marks?
They collide.
They actually collide. And in how many years does it take to equal 1.3 million? 10 point what? 996, which you would probably round up to what? 11 years. Do you guys see that? I put in our model up here. The 1.04 times 1.025 to the x, and then the next one I said we want to know when that is going to be equal to 1.3, and we're just looking for their crossing right there. Okay, so you guys are going to say approximately how many years? Whoops. That is a great example. I'm going to tell you right now, if you can understand example 2 today, you're going to understand, well, that's the worst looking star I've ever seen in my life. There.
That's cheating.
We'll take some noise for them.
No.
Dang, they all got a star too.
It's okay. It doesn't bother me.
It matters.
All right, you guys got everything you need there? All right, kids, let's go to the third page here. All right, this is where things can kind of start to get a little tough, and I'm going to kind of do the first ones with you. Writing a recursive rule. Okay, this is the part where you need to know your start and what's next. And I'm not going to get terribly excited about this because it talks about sequencing and stuff. But what it says right up here for a recursive rule, you always have to tell me what you start with. So f of 0 is always equal to what, kids?
A.
And then you have to write down that f of n is equal to whatever your growth factor is, r, times f of n minus 1. So here's the deal. Guys, when you start this out, for your start right here, f of 0,
Well, think of it this way. If I threw 0 in, kids, if I threw 0 in, what would 7 to the 0 be? 1. And then 1 times 4 is what? 1 times 4 would be what? This number out front is always like your start value. So you always write down my recursive rule is f of 0 equals 4. Okay, it's saying we are starting at 4. Then your rule becomes the following. After this, you write down f of, in this case, x for our rule. And we'll go n. I don't even want to do that. I'm going to go x with this. F of x, because I use x up there. F of x is going to equal, all right, check this out, kids. What's your growth factor here? You just put this out front, 7 times, and then you just write it like this, right up here, f of x minus 1. And that's all you have to do for a recursive rule. And let me show you why this is true. Because your first term really, kids, is the start here. What would 1 minus 1 make here? 0. So this is really f of 0, which is what value? What is f of 0? 4, and this becomes 4 times 7, which would be what? Well, you would tell me 28, right? And it's the same effect as putting a 1 up here. What's 7 to the first still equal to?
1.
7 to the first, not 0. 7 to the first. What's 7 to the first? 7 times 4 more would be what? 28. Now this will make more sense when we start looking at some sequences tomorrow here, but I just want to make sure you know how to write the rule. So you guys, to wrap up here a little bit quickly with this one in example 4, you guys at least tell me how to write a recursive rule for this. What would I call f of 0 here, first of all, kids?
9.
That's the start value. Okay? Then you simply say, for, in this case, this would be f of what variable, kids? We're using t up there, right? F of t would equal then, what's my growth factor, kids? 1/3. Then you write f of t minus 1. Just learn how to write these first. Okay? Okay, this is new for you guys. This is very new for you. And you'll see more why this works here as we get into some of the sequences on the next few pages here. But kids, first things first. This first one is always where you do what?
Start.
And that's the front value. And then down here, you bring your growth factor down here, or your rate of change, times f of whatever variable minus 1. This will be like your next term right here all the time. Okay? All right, kids, I think that's a good place to stop. No homework tonight, and we'll finish this up tomorrow. You guys cool with that? If I didn't get practice 1.5 from you today, make sure I get it sometime later today or first thing tomorrow from you. JMC's up to date again, so check that out. You guys are doing a phenomenal job. Keep up the good work, okay? Levi, do you have study hall at all today?
Not today, but tomorrow.
What hour?
Second.
Any chance maybe you could come down and visit with me second hour a little bit tomorrow?
Sure.
Try and work on a plan to get you caught up. Okay,
Yeah.
do you, what you got, Gracie?
When I did that one again, I got
You gotta go 4 to the 4th power now, kid. So the cube root of 64 first. Do that for me. No, the cube root of 64 is actually...
oopsies, it's 4.
Yep, so now you're gonna take 4 to what power?
4.
See what 4 to the 4th equals.
Oh.
Okay, now?
14 minutes?
Thanks, kiddo.
It's in Denver, so I might just be able to see like the end score.
Well, they're fired up over there today, aren't they? Holy cow.
Yeah, I'm right.